Hi, I am Rahifa Ranum from University Technical Malaysia, Melaka. In this video, I will show you one example of Fourier series. Given a function ft equal to 0 when t from -2 to 0, ft equal t when t from 0 to 2. This is a periodic function of period t is 4. The first question is sketch the function over the interval from -6 to 6. Determine whether the function is even, odd, or neither function. The second question is find the Fourier series of the function. The solution to the first question. This is the sketch of the function of ft over the interval -6 to 6. From t -2 to t equals to 0, the function is 0. Therefore, we're going to plot from t from -2 to t equal to 0. The function is 0. In the other interval, t from 0 to 2, the function is t. So this is how we plot the function of ft from -2 and 2. To extend the sketch over the interval -6 to 6, we just need to repeat the plot of the function identically. Based on the plot of the function, we can see that the function is not symmetric about the y-axis, and the function also is not symmetric about the origin. Therefore, the function is neither even nor odd function. This slide shows the solution for question 2, where we need to find the Fourier series of the function. Based on the function, the value of L is 2. Since the function is a neither function, therefore the appropriate formula to obtain the Fourier series is the Fourier series formulas. The next step is to calculate the Fourier coefficients A0, AN, and BN. The formula of A0 is 1 over L, the integration of the function ft with respect to t from -L to L. Here, I have substituted the value of L into the formula. Recall that the function ft is a piecewise function with 2 intervals. Therefore, we have to solve this integration by separating the integration into 2 integrals. The first integral is when the function ft equal to 0 within the interval t from -2 to 0. While the second interval is to solve the integration of the function ft equal t within the interval t equals 0 to t equals to 2. We can see that the solution for the first integration is 0. By solving the integration of t with respect to t from 0 to 2, we obtain the Fourier coefficient A0 is 1. Here is the formula of AN. The formula of AN is 1 over L, the integration of ft cos n pi t over L with respect to t from minus L to L. Again, I have substituted the value of L into the formula of an. So by separating the integrals into two integrals, okay, we obtain the first integrals is the integration of 0 with respect to t from minus 2 to 0, plus the second integral is t cos n pi t over 2 with respect to t from 0 to 2. The first integration is equal to 0. In order to solve the second integration, we have to use the tabular method. So here is the tabular method where we need to differentiate the function t and integrate the cos n pi over 2t. By differentiating the function t, we get 1, and again when we differentiate the 1, we're going to get 0. Okay. Consequently, we have to integrate cos n pi over 2t 2 times. Resulting from the tabular method, the solution to the integrals is written here. The next step is to substitute the limits t equals to 2 and the limits t equals to 0 into the resulting of the integration. Let's recall the tips of identity trigonometry. The sine n pi is always equal to 0. Therefore, the first term is 0. Cos n pi here is equal to minus 1 to the power of n. Thus, the final answer of the Fourier coefficient an is equal to 2 over n pi squared times minus 1 to the power of n, comes from the second term, then minus 1 comes from the third term. So now we are going to find the Fourier coefficient of Bn. The formula of Bn is 1 over L, the integration of ft sine n pi t over L with respect to t from minus L to L. Here, we can see that I already put in the value of L into the formula. So again, we have to separate the integration into two integrations. Between negative 2 to 0, the function is 0. And between the interval t 0 to t equals to 2, the function is t. Therefore, the second integration is the integration of t sine n pi t over 2 with respect to t from 0 to 2. The first integration is 0. In order to solve the second integration, we need to use the tabular method as shown here. From the tabular method, we obtain the solution to the integration is like what have been shown here. Substitute the limits t equals to 2 and t equals to 0 into the resulting of the integration. So we obtain, when we substitute t equals to 2, the answer is minus 4 over n pi cos n pi plus 4 over n pi squared sine n pi minus, when you substitute t equals to 0, the expression becomes 0. By applying the tips, the cos n pi is minus 1 to the power of n and the sine n pi is always equal to 0. So therefore, the answer for the Fourier coefficient Bn is equal to 2 over n pi negative 1 to the power of n plus 1. The last step is to substitute the Fourier coefficients A0, An and Bn into the Fourier series formula. The Fourier series formula is Ft equal to A0 over 2 plus the summation of An cos n pi t over L plus Bn sin n pi t over L, n from 1 to infinity. A0 equals to 1. An is equals to 2 over n pi squared minus 1 to the power of n minus 1. And the Bn is 2 over n pi times minus 1 to the power of n plus 1. So by substituting all the Fourier coefficients A0, An and Bn into the Fourier series formulas, we have obtained the Fourier series of the function Ft. That is the end of the explanation for example 1. I'll see you again in the next example. Thank you. The function Ft can be written in series. Ft equals to 0 when t from minus 2 to 0, and Ft equals to t when t from 0 to 2 with a periodic function of period 4 equals to this expression. Now, let's think how the Fourier series will look like graphically. In the next slides, I'm going to show you the graphical Fourier series for multiple n. Okay, I'm going to start with when we plot the series for n equals to 5. So remember that in the series, we have the summation n equals to 1 to infinity. Now, if I just solve the series from n equals to 1 to n equals to 5 and plot the series, this is how the graphical of Fourier series look like. So recall that the blue line here is the function Ft that have been plotted in question 1. So you can see that it's already look like a function Ft. If I increase n to 10, then we solve the Fourier series, the summation from n equals to 1 to n equals to 10, and plot the series. So we can see that it's getting better. The representation of the series to the function Ft is much better than the previous plot of n equals to 5. So what happens if we keep increasing the values of n? So in this slide, the plot is when we choose the n equals to 25. And we solve the series from n equals to 1 to n equals to 25 and plot the series. So you can see that the plot of the series looks almost similar to the function Ft. Last but not least, if we increase the n to 50 and we plot the Fourier series, so we can see that the series looks exactly similar to the function Ft. So this is what we want. We want the Fourier series to represent the periodic functions from a piecewise function Ft, so we can have a series that is similar to the function Ft. So I'm going to end the video here. I'll show you another example in the next video. Thank you for listening and watching. Bye.